Hey everyone, and welcome to This Explainer. Today, we're diving straight into the absolute foundation of our modern digital world. We often think the real magic of technology lies in these incredibly complex microchips, but the truth is actually much, much simpler than that. So think about it for a second. What is every single electronic device actually made of? Underneath all those fancy sensors and high-speed processors, literally everything is built from just three humble, simple parts that control the flow of electricity itself. We're talking about the resistor, the capacitor, and the inductor. Together, these three form the basic alphabet of all modern electronics. Okay, let's dive into this. Section 1, resistors, the current controllers. The resistor has these incredibly patient, methodical origins. Our story actually starts in Germany, back in the 1820s, with a schoolteacher named Georg Simon Ohm. At the time, scientists had batteries and wires, sure, but nobody really understood the mathematical relationship between electric current and the actual force driving it. So Ohm patiently spent years experimenting with wires of all different lengths and thicknesses. He carefully measured the current flowing through each and every one until, finally, in 1827, a remarkably clean mathematical pattern emerged. What Ohm realized was that the amount of current running through wire is directly related to the voltage, which is the driving force pushing it, and inversely related to the obstacles pushing back against it. He called those obstacles resistance. And that huge breakthrough gave us Ohm's law. Voltage equals current multiplied by resistance. To this day, it remains one of the most famous and fundamental equations in all of physics. So in his honor, the unit of electrical resistance is called the ohm. When you look at real macro photos of modern resistors, you'll see they are often these tiny little cylinders with brightly colored stripes painted around them. Engineers actually read those stripes exactly like a barcode, so they can instantly know the resistor's value without even having to test it. And these things are absolutely crucial. I mean, almost every circuit with an LED has a resistor sitting right next to it just to limit the current. Without it, way too much current would rush in and burn that delicate LED out in a fraction of a second. To picture this at a microscopic level, imagine a crowded hallway. If the hallway is super wide and totally empty, people, or in our case, electricity, can move through it really easily. That's your low resistance. But if that hallway is narrow and just packed with obstacles, people are going to struggle to get through. That's high resistance. Inside a resistor, flowing electrons are constantly colliding with atoms, losing just a little bit of energy each time, which usually just gets released as heat. All right, moving right along to section 2, capacitors, the electricity buckets. Now, while the resistor was born from really careful mathematics, our second component, the capacitor, has a much older and, honestly, a far more dangerous origin story. Back in the 1740s, this Dutch scientist named Pieter van Musschenbroek was trying to literally capture electricity inside a water-filled glass jar lined with metal foil. Well, in 1745, he accidentally touched the connected wire and got a massive, incredibly painful shock. It was so bad he reportedly declared he wouldn't repeat the experiment even if you gave him the crown of France. But without even realizing it, he had built the world's very first capacitor, the Leyden Jar. It wouldn't be until the 19th century that Michael Faraday finally explained the underlying theory behind what just zapped him. In Faraday's honor, the unit of capacitance is the farad. Seeing a real macro photo of modern electrolytic cylinder capacitors gives you a sense of their scale, but essentially, a modern capacitor works by using two conductive plates facing each other, separated by a super thin insulating layer called a dielectric. When voltage is applied, a positive charge builds up on one plate and a negative charge on the other. But because they can't cross that tiny gap, they just wait there, storing energy in the electric field right between them. The best way to think about it is like a bucket for electricity. A capacitor can fill up super quickly, and unlike a normal battery, it can dump all its stored energy out in one instant burst. This is exactly why capacitors are used in camera flashes. They charge up slowly, then boom, release all that energy in a split second. They're also absolutely perfect for smoothing out bumpy electrical signals and filtering out unwanted noise, which keeps the whole circuit perfectly stable. Which brings us to section 3. Inductors, the magnetic flywheels. Our third and final component was born from the strange, completely invisible link between electricity and magnetism. And the history here is just an incredible coincidence. In 1831, Michael Faraday over in England and Joseph Henry in the United States were both working on the exact same problem. Entirely independent of one another, with literally zero knowledge of each other's work, they both discovered that changing the current flowing through a coil of wire creates a changing magnetic field. and that field can push back to generate its own voltage. We call this electromagnetic induction. Because Joseph Henry discovered a closely related effect called self-inductance, the unit of inductance is named the Henry. Now, when you see real macro photos of a modern inductor, it's pretty unmistakable. You can clearly see these tightly wrapped copper coils wound around a core. When current flows through those coils, it generates a magnetic field. But the real magic here is that the inductor pushes back and actively resists any sudden changes in that current. So, the best way to visualize this is to picture a heavy flywheel on a bicycle. A flywheel naturally resists any sudden changes in speed, right? It just smooths your whole ride out. Well, an inductor does the exact same thing, but for electricity. If the current spikes, the magnetic field pushes back. If the current drops, the collapsing field actually tries to keep it going. This behavior makes inductors perfect for filtering out sudden electrical spikes, powering massive transformers across city power lines, and even tuning early radios. Now, what's really interesting about this next slide is how they interact. Section 4, the magic of combination. So on their own, these components pretty much do one simple job. A resistor pushes back on current constantly, no matter what, just like trying to walk through a crowded hallway. A capacitor pushes back only when the voltage is changing, basically storing charge like a bucket. And an inductor pushes back only when the current is changing, acting like that heavy magnetic flywheel. But when you start combining these distinct behaviors, man, that is where the real magic of modern electronics happens. Put a resistor and a capacitor together, and you build a timing circuit exactly like the ones they used in old digital clocks. Combine a capacitor and an inductor, and you create a filter that can pluck one single radio station out of thousands of invisible frequencies in the air. Combine all three together, you get the incredibly precise power control systems that run every smartphone charger, Wi-Fi router, and electric car on the road today. It's honestly amazing to take a step back and reflect on their wildly different origins. Everything we use today is designed by modern engineers standing on the shoulders of a patient schoolteacher meticulously measuring wires, a Dutch scientist who accidentally shocked himself trying to bottle electricity, and two curious scientists who made the exact same discovery an ocean apart. Basically, curiosity, extreme patience, and a little bit of dumb luck gave us the tools to build the future. Nearly 200 years later, they are still doing the exact same jobs, just quietly, by the thousands, tucked right inside the phone in your pocket. Which leaves us with a pretty thrilling question. If just three simple components, the resistor, capacitor, and inductor, can build the entirety of our modern digital world, what undiscovered combinations of simple ideas are waiting out there to build the next one? Thanks for joining me on this explainer. Keep your curiosity sparked and keep learning.